Get ready because the shipping industry is ripe for disruption. You're listening to Autonomous Ships Headquarters Podcast with your host, JP.
Everybody, welcome to Autonomous Ships Headquarters Podcast. The goal of this podcast is to introduce to you people and companies behind digital revolution that is transforming the shipping industry. I'm your host, Juraj Pavlica, or just JP, and today's guests are Mr. John Townsend and Mr. Dieter Gabriel. John is the VP Technology Policy, and Dieter is Marketing Manager of Europe, Middle East, and Asia of Velodyne. And Velodyne is a US company which is famous for their iconic lidars called pucks. If you ever seen a picture or video of a autonomous car, except Tesla, you've probably seen Velodyne's lidar on top of it. This technology is finding its way into the maritime industry, and today this gentleman will tell you more about it. So, without further ado, meet John and Dieter. John, Dieter, welcome to the show.
Glad to be here.
Yeah, thank you.
Thanks for being here. Velodyne is a well-known company, especially for the people who are into autonomy, into robotics. But before we dive into more technical details, why don't you guys tell us a little bit more about your career path and how you ended up working in Velodyne?
Sure. So I'm John Townsend. I'm a VP of Technology and Policy. I deal with the intersection of the technology to policy and regulators. My background is in everything from full ocean depth submarines to ROVs, AUVs, robotics integration into different platforms. Worked for companies like Google, Intel, projects out of NASA Ames, so on and so forth. So just always been fascinated by this new wave of technology. The lidar system becomes the vision system for the robotics industry.
Yeah, I'm Dieter Gabriel. I'm the marketing manager for Velodyne, overseeing our business development in the area of Europe, Africa, and Middle East. And I've got a background in namely photogrammetry, image processing, and navigation technologies.
Very interesting. So why don't you, for the beginning, explain us a little bit what lidar is and how lidar work, since this show is all about autonomy in marine sector, and lidars are, at least in the civil applications, are not that used and well-known sensors as, for example, a GPS. So why don't you please explain a little bit how lidar works?
Okay. The term lidar is sometimes not so well known in Europe still. At the end of the day, it refers just to laser scanning. And LiDAR stands for light detection and ranging. So the physical principle behind the LiDAR or laser scanning technology is quite simple. So you have at least one laser diode or a bunch of laser diodes, and we are sending out light. In our case, if we talk about Velodyne LiDAR sensors, it is a so-called time of flight mode. So what basically happens is we send out a light pulse, somewhere it hits an object, it creates a reflection, and you get a reflected signal back. So that's principally all. So from the basic level of physics, it's quite easy. So the problems arouse from how you treat the data, how you process the data. That can be much complicated, but the overall principle is very, very easy to understand.
Sounds very, very similar to how radar works. So radar is one of the components well known for mariners. So you send a signal and receive a feedback. What I like the first logical question is, how does the weather conditions affect capability of these sensors?
Yes, all of our sensors, for instance, are so-called multi-beam or multi-channel 3D LiDAR systems. That means that we do not rely on one single laser, but we combine at least 16 in a row You have 16, 32, 64, or even up to 128 laser channels. So this does mean we scan the area we want to detect with our sensors with a lot of laser signals. And also, usually all the sensors are rotating sensors, so they give you a 360-degree view around the center of the sensor, so they are rotating in a 360-degree field of view. That means when you switch on the sensor and detect the environment, you see everything around you. And you do it with a lot of signals, with this so-called multi-channel approach, and this causes some benefit. Benefit is not only that you get a good resolution, but you see a lot of details from what you're scanning around you, but also that you send out millions and millions of photons, the hidden object, and you get some reflection back, so you get information about your environment with an enormous degree of details. And the biggest of our sensors, the most capable, gives you back 9.6 million laser points per second. So if you now imagine you use the sensor in bad weather conditions, like in pouring rain, in dust-affected environments, in snow,
fog, haze,
So you have so many photons going through that kind of weather, penetrating even rain or dust, and so that always a lot of the things, the information you send out, you get some signal back. And now you can filter it, you apply a filtering, and you end up with a good quality of your scanned environment, even under bad weather conditions. Okay, a good allegory might be, you can compare it with a human eye. So your capability to see your environment is affected by rain or something else as well.
Of course.
If it's pouring down cats and dogs at a certain end, you do not see that much, and if you're traveling in a car, at a certain point you have to stop. And that's fairly the same with a laser, but compared to other technologies like standard camera systems, we can handle use the instrument to detect our environment, to recognize objects in a much better way.
But how, for example, what is the frequency of these lights that you're emitting? This is outside of the visual spectrum, I guess?
Definitely.
And the follow-up question is then the color, for example, of the material or the object that you're detecting has to do anything with...
So the signals of the laser beams we send out are invisible to the human eye. That's the first point. And the more important fact is that all the energy, the signals we send out is eye safe. So this is a prerequisite for operating our sensors in, for instance, urban environments or in any environment that a lot of people are moving around. So it's so-called laser class 1, so it does not harm human eyes. And another important point is...
So the reiterance or the reflection of the object as you're sending the laser out, it actually is coming back and giving you a signal of its reflectivity of that object. So a brighter object is going to give us a more intense, a dark object is going to have a certain amount of absorption. We can actually measure that, and we can actually image that part of it. So I can tell you in one of the ways that we put out data what the actual color temperature is.
How reflective the object is.
Absolutely, and if you have a very reflective surface, then it's going to come back as a very intense image.
With less damping.
We then modulate that as to how much energy we need to send out to be able to receive the energy back, so that we can now modulate that process.
So you can reduce the energy, for example, if it's not needed to...
Yes.
Okay, interesting.
And an important fact is that for quite a long time, detecting objects with a low reflectivity, quite dark object, was a real challenge for the laser scanning technology. And so the degree of the reflectivity of the object gives you an indication how good, how capable actually your lidar system is. And all of our new sensors, for instance, come with the so-called 10% reflectivity rate on a dark object in the maximum range. That means that you can detect in, say, 200 or even 300 meters small objects with almost no reflectivity, and you can be sure that you really get the information about this object. This is utmost important, for instance, for autonomous cars. So if there is a certain debris on the road, think about a lost tire that is black, and you want to detect this object as soon as possible in order to apply some measures. Yeah. So it is a question of safety.
Definitely. So that's a very good development and a property of your product. This is super important. What about, you mentioned also the range. What is the usual range that we can expect from a lidar?
So range is defined as how we utilize it within the automotive industry. Because again, as Dieter was talking about the 10% reflectivity of the black object at distance, in R128 we're looking at 300 meters. It's about the ability to see that dark object at a traveling speed that gives you enough time to respond. So it's a framework that we use within the automotive industry that isn't necessarily the same in marine applications, because I may be able to look further, but my time and what I need to reflect on is usually a larger object at a greater distance, as well as I'm also traveling at a much slower speed. So when we actually create the specs, they're specs that we're using for the automotive industry. It's not necessarily a framework that we're using for the marine industry. So the applications may be different. But if you just take those general specs, it means that within that close environment, I can give you a very detailed image of what you're looking for close up for autonomous docking. There's multiple applications of looking at things in your pathway or around your environment.
Another example is, we talked about capability to penetrate rain, to handle certain environment conditions. So there are a lot of applications, especially in the maritime environment. For instance, if you think about autonomous guided vehicles or steering of trains in a port environment, at the dock of a maritime facility, for instance. And you might say that for a lot of applications, maybe 40 or 50 meter range might be sufficient. But it is very important that you have systems also with quite low power consumption, actually, that have a very good range, because if they come with a range of 200 meters or even more, possibility to handle bad weather conditions is much better. Because what happens if you use a sensor when it's raining, its range decreases. So it affects your capability to see through a certain distance or to recognize through over a certain distance objects. And if it starts to rain and you use a sensor with maybe 40 meter range, you quickly end up maybe with 10 meters only. But if you got a more powerful laser, that means your sensor will decrease as well, but you still can see in a certain rainy environment maybe up to 80 meters.
Get it. So maritime will benefit from higher performance required in automotive. We can see already, especially when it comes to
some crossovers. There's crossovers into multiple industries. Again, it really comes back to that. The eyes for the robot.
And speaking of eyes for the robot, ship is let's say that we have an autonomous ship which is going through some rough seas, or for example in short sea application, it doesn't matter. But the ship has quite some relative movements that is undergoing. So we have heave, we have roll, we have all kinds of things. Vibrations as well. How does a lidar that is fixed on such a ship can compensate these movements? So because then the ship thinks that the whole world is moving, but actually the ship is moving. How is that arranged?
Here is another benefit of our kind of technology. Our technology approach gives you 360-degree lidar. So we have lidars that rotate with a frequency of up to 20 hertz, so that means 1200 rounds per minute, and they are capable to detect with one rotation the whole environment. And you get a so-called vertical field of view of up to 40 degrees. So you see in one approach a huge portion of your total environment completely 360 degrees around. And that with aforementioned multi-beam approach with up to 128 laser channels. Now, what happens if you're affected by a lot of roll and pitch effects and other kind of movement is that you get a depiction of the environment where you get a crossover of the individual laser lines. So they move up and down, and one spot that was hit by, say, laser channel number 10 is now in the next moment covered by 11 or 12 and so on. So that means the multi-channel approach gives you the benefit in that sense that you can say the more movement you apply to the sensor relative to the objects you want to detect, the better is the spatial resolution, the depiction of the environment. And if you combine now such a sensor with an inertial measurement system, you're fine. So it is an measurement instrument ideally suited for moving platforms, for ups and downs to compensate all these things.
Very interesting.
Yeah, we even have some clients who actually will take and spin our lidar as well as it's already spinning outside. So it's a matter of what you're trying to accomplish and what your goals are. But basically, as it's fixed alone, it's already dealing with that motion and it enhances its ability.
Is this Is this inertial measurement unit part of the lidar itself? So is this something integrated in the sensor, or this is needed to be added as an additional standalone device?
Principally, it needs to be added, but due to the fact that you get a timestamp from the GPS measurement to every point, connected to every point we collect with a laser scanner, it's a kind of seamless integration. It needs some further processing, some immediate processing, but within a few milliseconds, you get it completely processed, and you, if you think about real-time kinematic approaches, you end up quite quickly with a fully referenced scene.
Makes sense. Makes sense. Let's switch gears a little bit from technical to business. Like, could you tell us, please, what kind of applications are you currently seeing in the maritime arena with lidar? What kind of solutions, and you can tell us maybe what customers or what they're doing with lidars.
So I think the automation portion of the marine industry is still new and actually developing. There are lots of test programs out there that are actually taking this first step, very much similar to what's actually happened in the automotive space. So we're at the early days of this development.
So everybody's very cautious, and
everybody's trying to figure out, okay, what do I do? What do I use? How do I actually make this work? And they're following examples that are being developed in the automotive space. So it's a natural tendency to actually grab some of the tools that are there. At the end of the day, it's always going to be a fusion, or it should be a fusion of different technologies.
Of course.
You, as your body, actually have multiple sensory inputs that help you actually function through life. The same thing is true with autonomous platforms. So it'll be a combination of lidar, cameras, radar, fusing that information together to be able to create a platform that can perform in these environments, right, safely and continually. One of the early places that we see as opportunities is understanding that spatial awareness within the vessel and its surroundings. So that could fit into security, that could fit into actual autonomous docking, it could fit into actually movement, but it's understanding what's happening around that space that's important. Dieter will tell you about an application that we're using in the crane applications, which is an excellent application for LiDAR. We've been historically in autonomous mining, in UAVs, in industrial applications, as well as automation in military and, of course, cars.
I'd like to hear more about this crane applications. Because when I think a little bit about it, I see that, for example, for containers, the problem is much simpler than, for example, for bulk. Is there something similar happening in industry? Like, can we use it?
Meanwhile, we can look back onto nice reference cases regarding bulk handling, for example. So, for instance, quite close here to Amsterdam is the port of Rotterdam, just 30 kilometers away, I think. We have there a nice installation where 4 or 5 bulk handling cranes, huge ship-to-shore cranes, are being handled fully automated since almost 5 years now, I think. And so what we do is a ship comes in, and first of all, the LiDAR sensors scan the boat incomplete. So this is done in order to get information what's on board of a ship, not only the shape of the ship around the hull, but what is on deck. Are there any obstacles? If you operate a grab, an automated grab, it must not collide with any things on top of on board of the ship. So in the second approach, the sensors identify the compartments, the bulk compartments. And so in the third approach, the grab is automatically placed about the next compartment in the row, and they in a fully automated way now start the unloading of the bulk material, the iron or coil, whatever. And another thing is, imagine you have some kind of material that may slip. So you cannot just put a grab down perpendicular with perpendicular movement into the compartment room and begin unloading. But because at a certain point the material might slip and bury the grab. That would be a very bad effect.
Interesting.
Because at the end of the day, you would have to bring a tractor down into the compartment and try to
release the
grab. That would be very bad. And not.
It's just a lengthy. It's, indeed.
It would be sheer catastrophe. But so in the end, you have to bring the rope that the grab is tied to into a controlled movement. It has to rotate and it has to start to get the bulk from the side of the compartment without damaging anything in the ship. Yeah, so you have a controlled rotating movement, and the control is done. This is all supervised by the data from the laser scanner, because you get a 360-degree kind of point cloud. You have everything under control. You always see the position of the crab relative to the compartment. You see the position of the crab relative to the surface of stock of bulk, whatever, pile of bulk.
You can map this confined space.
This is being controlled from a central monitoring spot where they operate and control 5, 6, 7 cranes. We have the same scenario at Hansaport in Hamburg running. A lot of iron ore harbors are being equipped with that kind of technology in Australia, and these are very sensitive applications in that way that you cannot afford a long standstill of operations. If you are affected by problems, it would quickly cost millions of dollars if you have to do some longer repair things. So our sensors have to be secure, and they have to operate for a long time under all weather and temperature conditions.
Yeah, that's especially important in maritime when it comes to type approvals and IP rating and all of the rest of the certificates. Yeah, to wrap it up, What's the plan for Velodyne in Europe, in maritime? Of course, it's to expand the business and to sell the units, but I see that the maritime now is kind of your also strategic industry that you want to penetrate. That's why you're on this fair. So can you tell us a bit more about your future plans?
So we're very engaged in the maritime industry. We actually have an R&D department that also has a section that deals with adaptive suspension technology that's just been one of its patents has just been approved in Europe. So we have an interest, and we see an opportunity for our technology to be a big part of the autonomous boat program as it actually goes forward, or autonomous shipping. We need to actually do things smarter and more productive in order for us to be able to deal with the transportation of our resources. The globe is actually populating. We need to be able to move goods and services much more effectively. This is just another mobility platform for us.
Excellent. That's a great point for end. So thanks again for being on the show, and I wish you all the best in your future business.
Thank you.
Thank you so much. We appreciate the opportunity for having an interview.
Thank you.
And that was all for today's episode. Thank you for listening, and don't forget to follow us on Twitter. Our handle is @AutonomousShips. You will also find us on Spotify, YouTube, and LinkedIn. If you like this episode, please share it. If you have any comments, feel free to send us an email. And that's it. Until next time, my friends. Take care. Hoi hoi.